Titrations are simple yet effective experiments to determine the concentration of a solution. These experiments are called volumetric analyses. Here is a simple setup for titration. An Erlenmeyer flask holds a solution called the analyte of unknown concentration. A few drops of indicator are added to the analyte. An indicator is a chemical that is not part of the reaction but will change color when the reaction is complete. The Erlenmeyer flask is placed under a burette, which is held in place by a burette clamp and on a support stand. The solution in the burette is called the titrant and is of known concentration. The burette has graduations to measure the amount of titrant that has been dispensed. The titrant is introduced to the Erlenmeyer flask by opening the valve or stopcock. The equivalency point is when the exact amount of titrant is added to the analyte as per their stoichiometric ratios in the balanced equation. Ideally, you would choose an indicator that will change color at a pH near the equivalency point. The point where the indicator changes color is called the end point. The analyte is the solution of unknown molarity, but we do know the volume that we started with. And we also know the volume and molarity of the titrant used in the reaction. Therefore, we can solve for the moles of the titrant used in the reaction. We can use the balanced equation to convert the moles of titrant used to the moles of analyte present in the original unknown solution. And finally, we can solve for the molarity of the analyte by dividing the moles of analyte by the volume of the unknown solution used. But wait, how do we know the true concentration of the titrant? Before doing a titration experiment, we need to run a standardization of the titrant. To standardize the titrant, we'll need a known mass of solid. If we know the mass, we can always convert to moles, and place the solid crystals in an Erlenmeyer flask. And we'll add water to dissolve the crystals. Remember, the amount of water added doesn't concern us since we know the moles already present. Next, we'll add a few drops of indicator, which will change color near the pH of the equivalency point, and place the flask under the burette. Open the valve or stopcock to dispense the titrant into the Erlenmeyer flask, until one drop turns the solution a different color. This is the end point. The moles of analyte are known. We can use the balanced equation to convert to the moles of titrant. Now we know the moles of titrant. We can measure the volume of titrant used from the burette, and finally find the standardized molarity of the titrant. A student standardizes an NaOH solution with KHP, potassium hydrogen phthalate. A 0.7137 gram sample of KHP is neutralized with 24.59 milliliters of the NaOH solution. What is the concentration of the NaOH solution? The NaOH KHP stoichiometry is a 1-to-1 ratio. For this particular problem, we are reacting sodium hydroxide with KHP. In this reaction, I'm just putting products on the product side. The problem already tells me, and this is pretty common for most general chemistry labs and problems, the sodium hydroxide KHP ratio is 1-to-1. So we know the stoichiometry already. And we want to solve for the molarity of the sodium hydroxide. We want to standardize the sodium hydroxide. The molarity is the moles of sodium hydroxide per liter of solution. And so we want to fill in these blanks here. Now we already know one of them, the liters of solution. This is the amount of sodium hydroxide it takes to neutralize the KHP. So this is the volume, the 24.59 milliliters. Since we're dealing with molarity, we want to get this in units of liters. So that's what I do right here. So the next thing we'll do is find out, okay, in this volume of sodium hydroxide, how many moles of sodium hydroxide are present. So in the problem, they tell us we have 0.7137 grams of the KHP, and we'll convert that to moles. And the molar mass here is 204.22 grams of KHP. And I'll go to 2 decimal places, which is pretty common. And then we'll do some stoichiometry. So here's the moles of KHP present. We'll convert to the mole of the NaOH and cancel mole of the KHP. And again, in the problem, we're told that the stoichiometry is a 1-to-1 ratio. So pretty simple. We found our moles of NaOH. To 4 significant figures, I get 0.003495. So now we'll find the molarity, which is the mole of the sodium hydroxide divided by the volume of the solution. So this is the titrant. This is how much was used, 0.02459 liters. So to 4 significant figures, 0.1421. A volume of 18.50 milliliters of KOH is used to neutralize 0.4128 grams of KHP. What is the concentration of the KOH solution? Like the sodium hydroxide, the potassium hydroxide KHP stoichiometry is a 1-to-1 ratio. Let's just do one more standardization problem. In this example, we'll standardize KOH, potassium hydroxide, against KHP. Again, the products don't really matter. The question tells us the stoichiometry is 1-to-1. Just like in the last example, the volume of our KOH, our titrant, is given to us. This is how much volume is used to standardize the KHP. So I convert to liters. Now I want to find the moles of the KOH present. So in this example, we start with 0.4128 grams of the KHP. I'll convert to the moles of KHP. And the stoichiometry is 1-to-1, so we can convert to the mole of the KOH. So this tells us the amount of KOH that was required to neutralize the KHP to 4 significant figures. This is 0.002021. And so now we can just put them together to find the molarity, the standardized molarity. And to 4 sig figs, 0.1092 molar. 5.00 milliliters of a vinegar solution, which is acetic acid in water, is titrated with 18.35 milliliters of a standardized 0.188 molar sodium hydroxide solution. What is the molarity of the vinegar solution? Here we have a classic general chemistry question. This is a classic lab in general chemistry, which is the titration of vinegar or an acetic acid solution with sodium hydroxide. In this example, we're told that 18.35 milliliters of a sodium hydroxide solution with a standardized molarity titrates or neutralizes a 5 milliliter sample of the vinegar or acetic acid. And what we want to do is solve for the molarity. So for this problem, we do want a balanced equation. So we'll do a double displacement reaction. Sodium acetate will be one product. And for Arrhenius acid-base reactions, water will be our other product. Conveniently for us, this is all a 1-to-1 ratio. So what we'll do is we'll take advantage of this stoichiometric ratio here. Let's find the moles of the sodium hydroxide. So in my first step, I'll convert the milliliters to liters. And the reason I do that is because I want to cancel the liters and convert to mole of the NaOH. Mole-liter relationship, of course, that number is right here. This is the molarity. And then here I'll convert to the mole of the acetic acid. So this ratio is 1-to-1. And so there you have it. I'll go to 3 sig figs. So there are my moles present in my 5 milliliter solution. Now let's take a look at the volume here. So the volume of the acetic acid is 5 milliliters. If we want to find the molarity, we have to convert this to liters. So we'll just divide by 1,000, and that'll give us our volume in liters. So now let's put it together. So our molarity, 0.690 molar acetic acid. What is the percent by mass of the vinegar solution? So we'll pick up where we left off here. So we have the molarity of the acetic acid. Another classic example in general chemistry is to find the percent by mass. Now, if you look at percent by mass, the mass of the acetic acid for every mass of the vinegar solution. Now, for this problem, we need to know the density of the vinegar solution. And so the density is usually given to you in your lab notebook or in your textbook. The density is about 1.01 grams per milliliter. And so that's going to allow us to convert the volume into the mass. What about the mass of the acetic acid? So what I tell my students, this is my recommendation, let's go straight to our molarity. So this is the molarity of our acetic acid. So let's rewrite this, 0.690 mole of the acetic acid for every liter of solution. And so you can see what we're going to do here. We're going to convert the numerator and denominator into the mass. So let's do the mass first. This one is pretty simple. Let's convert to the grams of the acetic acid. Cancel the mole of acetic acid. Grams per mole is the molar mass. So for acetic acid, we'll go 60.06 grams per mole. And so now we have the mass of the acetic acid. Let's do the same thing with the volume. Now, I have the density in grams per milliliter. So what I'll do here is I'll convert the unit of liters to milliliter. And you can see where I'm going with this. Then I'll convert milliliters to the gram of solution and cancel the milliliter. And you can see right here, that's the density. For every 1 milliliter, the mass is 1.01. So this ratio is 0.0410 gram of the acetic acid for every gram of solution. Now to get the percent, of course, the gram over gram cancels, so that unit cancels. Percent, of course, is just a unitless ratio. And to get the percentage, of course, we'll multiply by 100. So this winds up to be 4.10%. And so this is the percent of acetic acid by mass in a vinegar solution. What volume in milliliters of a 0.230 molar sodium hydroxide solution is required to neutralize 25.0 milliliters of a 0.177 molar sulfuric acid solution? Here's an interesting problem, a little bit different than what we've seen so far. We have sulfuric acid being neutralized by sodium hydroxide. The sodium hydroxide is standardized. We know the molarity there. But we also know the molarity of the sulfuric acid. So what we're asking is, if we know the concentration of the sulfuric acid, how much sodium hydroxide is required to react with 25 milliliters? How much sodium hydroxide is required to neutralize this volume of sulfuric acid? So we're actually looking for our volume of titrant or sodium hydroxide. So in order to do this, we do need a balanced equation. So for an acid-base reaction, we'll do this double displacement. Sodium sulfate will be one of the products. And of course, for these Arrhenius acid-base reactions, water will be our other reactant. And we'll balance the equation. We'll put a 2 in front of the sodium hydroxide and a 2 in front of the water. And so now we can solve for our problem. Okay, interesting problem. I'm going to do the stoichiometry starting with the sulfuric acid. So let's find the moles. Let's take advantage of this mole to mole ratio. So I'll start with my 25.0 milliliters of the sulfuric acid, and I'll convert to liters. And I want to convert to liters because I want to take advantage of the molarity that's given to us. So I'll convert to the mole of sulfuric acid and cancel the liters. That's what this is right here. Molarity is mole per liter. So you notice what I've done here. I've converted to the moles of sulfuric acid present. What I'll do next is convert to the mole of the sodium hydroxide. That's where we use the mole-to-mole ratio. 2 moles of sodium hydroxide react with 1 mole of the sulfuric acid. So now I've done it. I found the moles present. Now I can take advantage of my molarity for the sodium hydroxide. So notice what I'm going to do here. I'm going to keep going, and I'm going to convert the moles of sodium hydroxide to volume. Notice I'm converting to liters, and I'll cancel the mole of the sodium hydroxide. Again, mole-liter relationship, that's the molarity, which is given to me in the problem. And so now I've done it. I found the volume. Now, in most general chemistry classes, we're working on a small scale, milliliters. So, of course, what I'll do in this next step, and I'll continue down here, I'll convert the liters into milliliters. And so the liter will cancel with this liter here. And so the answer I get here, 38.5. I'll go 3 significant figures because of my molarities. So what does this number represent? This is the volume of titrant, sodium hydroxide, required to react with this sulfuric acid to neutralize it, assuming that our titrant has this standardized molarity. The problems thus far have been acid-base neutralizations. Before concluding, I want to do one oxidation reduction problem. Oxidation reduction reactions occur when an oxidizing agent reacts with a reducing agent, and we can determine the concentrations of unknown solutions. A 50.00 milliliter sample of solution containing iron 2+ ions is titrated with 22.62 milliliters of a 0.0450 molar potassium permanganate solution. The permanganate oxidizes the iron 2+ ions into iron 3+ ions. What is the concentration of iron 2+ in the original solution? Assume the reaction occurs in an acidic solution. For this reaction, we need a balanced redox reaction. I strongly recommend visiting this playlist, which contains examples of balancing redox reactions in acidic and basic solutions. Here is the balanced redox reaction for this example. We're interested in this 5:1 mole ratio. In this example, we have 50.00 milliliters of solution that contains iron 2+ ions. Now, this isn't an acid-base reaction. What happens here is we have a redox reaction. What we can do is we can find the molarity of the iron 2+ in solution if we can react the iron 2+ with permanganate. Permanganate will oxidize the iron 2+ and turn it into iron 3+. And using the right indicator, we'll have a change in color, and that will tell us when we reach our equivalency point or end point. What's concerning for us here is this stoichiometric ratio and our permanganate, which is our titrant. So the problem tells us that 22.62 milliliters of the permanganate solution is used. So let's convert that into liters. And then what we'll do is we'll convert this into moles. So notice very similar to our acid-base reactions, and we can do the same thing for our redox reactions. So in the problem, this is given to us. The molarity of the permanganate is 0.0450 moles per liter. And then what we'll do is we'll convert this into the mole of the iron 2+ ions. And this ratio is 5:1. And so there we go. We get an answer here of 0.005090, running out of space there. That's how many moles of the iron 2+ are present in solution. So what is the molarity? It's the moles of the iron 2+ divided by the volume of solution. In this case, 50 milliliters. 50 milliliters is a 0.05 liter solution. So I convert that to liters. And so the answer here, 0.10. And this is pretty common. This is necessary, let's say, for environmental science, if you want to find certain ions in water or in the soil, or perhaps biological in a lab. What is the ion concentration in the blood or the alcohol concentration in the blood? And so we can do that by redox titrations.